Here's what we got to last time. We had talked about radical bromination, and I had mentioned that it was selective for forming the more substituted bromide, and that is because you go through a more stable radical intermediate. So remember, the first step of radical bromination after the initiation step is hydrogen atom abstraction, and bromine radical selectively abstracts the most substituted hydrogen so that you can make the more stable tertiary radical intermediate. And so this is a similar rule to rules you've learned earlier about carbocation stability, and it explains the regioselectivity of radical bromination. Now, interestingly, if we take the same starting material and instead we use chlorine, Cl2, you can still do a radical reaction, but it turns out with chlorine, you get a mixture of products. So you get one in which the chlorine is on the sort of methyl carbon. You get the blue tertiary chloride, and then you get a mixture of the remaining secondary chlorides. In other words, radical chlorination is not selective. You expect a mixture of those products. I will add at this point that I'm showing those radical addition products with straight lines, no dashes and wedges. And the reason I am doing that is because you learned that the radical is sp2 hybridized at the carbon-centered radical. The singly occupied molecular orbital is a p orbital, and that addition step can happen from above or below. So every place where there's a chlorine, we expect to get, if it's a stereocenter, both configurations. And in some cases, this gets complicated. In the orange and blue products, those are not stereocenters, so no big deal. In the pink and the purple products, now both carbons are stereocenters, and you would expect to get both configurations at both carbons. Kind of weird because the methyl, the carbon that's attached to the methyl group, the tertiary carbon, isn't a stereocenter to begin with, but as soon as you install the chloro at that adjacent carbon, it becomes a stereocenter. So you're expecting both configurations at both stereocenters. By drawing this, I represent 4 products. Okay, same thing here. Now here with green, these 2 carbons are still no longer they're no longer stereocenters. The molecule's not chiral, but there's 2 distinct stereochemical possibilities. One where methyl and chloro are cis to each other, and the other where they're trans to each other, and again, you expect to get both. So radical chlorination is kind of a mess, and that's why people don't do it a lot. The question we need to answer is why? Why is bromination selective, whereas chlorination is not? Before we answer that question, anything you want to ask about what we've just done? Yeah.
Just a little bit about the format. So just to clarify, with radical, like halogen or whatever, do you put the regions on the top and then H new on the bottom?
So above the arrow, below the arrow generally means nothing. I just needed the space.
Okay.
Yep. What else? Okay, yes.
Which were the ones that had multiple variations, but you just drew one of them? To represent all of them.
Oh, right. Pink, purple, and green. Pink and purple represent 4 each. Green represents 2. Blue, that's not a stereo center, so it's just 1. Yep, and same thing with orange. All right. So let's talk about why. And to understand why, you need to know that bromine radical is, oh, I'm going to get this wrong. Bromine radical is more stable than chlorine radical. By that we mean lower in energy. And the reason for this is basically the same reason that HCl is less acidic than HBr, or that Br minus is more stable than Cl minus. It has to do with bromine size. The unpaired electron is spread out over more space, therefore more stable than in chlorine. So with that in mind, let's imagine how this would play out in the first step, which is the radical initiation step. I'm gonna just use R dot as a radical, and we're going to draw propane as our alkane. It's got 2 different kinds of protons. It's got a proton on a primary carbon and a proton on a secondary carbon, right? So the radical abstraction step can give you either, you've got sort of 2 choices. Path 1 is to get the primary carbon-centered radical, and then path 2 is to get the secondary carbon-centered radical. I can push arrows for one of those. We'll show you path 1 where you get the primary carbon-centered radical, but I'll have you imagine the path to get the secondary primary carbon-centered radical, okay? Both of those paths, red path and blue path, are available to both chlorine and bromine. So let's see how they play out energetically. So here's an energy diagram. We're going to put starting materials here on the left, and it turns out for bromine, the starting materials, bromine radical and propane, are lower in energy than the radical intermediates. Okay, that has to do with bromine's stability. Now, for those radical intermediates, the primary radical is quite a bit less stable than the secondary radical. I'll just draw those here. But because the reaction is uphill, the reaction is endothermic, Hammond's postulate would tell us that the path that leads to the secondary radical that's more stable should go through a transition state that is more stable. Remember, Hammond's postulate is that a transition state most closely resembles either the starting material or the intermediate or the product to which it is closest in energy. In this case, the transition state that leads to the primary radical is very primary radical-like, whereas the transition state leading to the secondary radical is very secondary radical-like. meaning that the transition state that leads to the secondary radical is more stable than the transition state that leads to the primary radical, just as the secondary radical itself is more stable than the primary radical. So for bromination, the secondary radical forms fastest and is the major radical product, and then the major product stems from that primary or from that secondary radical. All right, questions about that reasoning? Anytime we invoke the Hammond postulate, it's a little bit confusing, a little bit convoluted. No? Or is this just a make it stop moment? It's like if we just don't ask any questions, maybe he will forget to tell us something, right? Okay. Let's draw this for chlorine. Radical chlorination. The big difference between radical bromination and radical chlorination is, that's not what we wanted, is that the chlorine starts out much higher in energy. The radicals are each going to be at the same place. I'm going to need a little bit more space. So let's now, chlorine is here. This is your starting material. Obviously, propane is the same energy on either side. This big energy difference is driven just because of the stability of chlorine. Here, because the reaction is exothermic, the transition state is going to be closer in energy to the chlorine radical starting materials than it is to the radical products. So you will see that the transition state leading to the primary radical versus the secondary radical, the transition states are similar in energy because they are very chlorine radical-like. They resemble that, both of those red and blue transition states resemble the chlorine radical, and as such, they're very similar in energy, okay? And that means there's no selectivity. They form at similar rates. All right, questions about that conclusion? So this is an illustration of a principle that people invoke all the time in organic chemistry. It's called the reactivity-selectivity principle. It's sort of a case-by-case principle, but here's how it works in this particular example. Chlorine is more reactive. In an exothermic reaction, the transition state from the chlorine radical looks very much like a chlorine radical and not very much like a carbon-centered radical. And therefore, there's no difference in how fast the two carbon-centered radicals form. Chlorine being more reactive is less selective. Bromine, Br radical, is less reactive. It's lower in energy than the carbon-centered radicals. That means the transition state in this endothermic reaction leads to the primary versus the secondary radical intermediate. That transition state looks very much like a carbon-centered radical, and stability differences will apply to the transition state too. So it's faster to go through the more stable transition state that leads to the more stable secondary radical, slower to go through the less stable transition state that leads to the less stable primary radical. And so the secondary radical forms fastest and we get selectivity. Bromine, being less reactive, ends up being more selective. Okay, questions? Yeah.
For chlorine, would we still mark like major products even though it's less selective, or just gonna be more selective?
Would you still mark major products, or would you just say no selectivity? I actually don't know what the numbers end up being. I don't know how non-selective non-selectivity is. For us, we just won't mark major products. And for the bromination, we'll only draw one. Another hand? Yeah.
So is it just kind of a general rule that the more stable that adding is like by itself, the less selective it is, or is it just for these specific?
Is it a general rule that the more stable something is, the more selective it can be? People like to think of it that way. I think that idea has been thoroughly debunked. You have to apply it on a case-by-case basis. Yeah. It's a tempting analogy, and the analogy is this. If you're really hungry, super hungry, you might not be as selective in your eating choices as you are when you're not quite so hungry. Frankly, I prefer chocolate chips whether I'm hungry or not, so that really doesn't work for me. But what else? Other hand? No? Yeah.
So all has to do with the energy of the transition state.
Yep.
Or the first one.
It has to do with which direction, uphill or downhill, the reaction is, and what the transition state more closely resembles.
So, because chlorine is a downhill transition state, does that mean most downhill transition states are going to have the same results?
So are most exothermic reactions going to have the same results? It honestly depends on how close the transition state is in energy to the starting material versus the product. Yep. Okay, so that's the radical addition reaction. Now, there's a few things we could talk about in our remaining time today. Give you a choice. We could talk about fire. We could talk about plastics and polymers, or we could talk about rancid oil. I think we've already talked about rancid oil, so yeah. Fire or plastics? Fire, okay. I told the 8 o'clock class this, and I sort of regretted it, but several years back, a student comes to my office, and I didn't know the student, but he's like, so dude, you're an organic chemist, right? And I'm like, yeah. And then he says, hear me out. I want to explode a turkey over Thanksgiving break. And I'm hoping you can tell me what combustible materials I should use to detonate this turkey. And I was like, okay, there's no way in heaven or hell that I'm going to tell you how to blow up a turkey. I'm not sure I know myself, but I'm not going to be held liable for the flying shards of frozen meat and bones that are going to go in all directions. He says, no, it's okay. Like in Texas, we routinely detonate turkeys. I don't know if that's true. But just because they do it in Texas doesn't necessarily mean, I love the great state of Texas, lived there for many years, served my mission there. But just because it flies in Texas don't mean it's a great idea, right? So anyway, I declined to tell him how to blow up a turkey. But we will discuss radical combustion today as a consolation prize. Maybe that's what I should have done. Instead of refusing, I should say, well, first you need to master all the radical reactions of combustion. Okay, so this is probably the among the things we'll talk about today, this is probably the part of radical reactions that you are most familiar with. Combustion is easy to write the overall equation for. It is really hard to draw what's actually going on. So methane, or natural gas, add oxygen, you get 1 molecule of CO2 and you get 2 molecules of water. Simple, right? That's combustion. You get CO2 and H2O. It turns out people that study combustion have identified hundreds of individual radical reactions that are going on to make that process happen. That's the overall equation, but that just describes the stoichiometry, and you can calculate how much energy is released, but that's not the mechanism. and the mechanism involves a series of radical reactions. I'll show you one, maybe two of them, and at that point you will tell me to make it stop, and I will, okay? So first, you learn about combustion at a very young age, and you learn that you need fuel, and you need oxygen, and you need an ignition source. So the fuel is the thing that contains carbon and hydrogen. Here's why you need oxygen. So you are used to drawing the Lewis structure of oxygen like this, and you are used to thinking about oxygen, molecular oxygen, as having 4 lone pairs. That's an oversimplification. It works, but if you do the MO theory picture of oxygen, what you end up with is 2 pi bonds for sure. Wait. So what you end up with in the Lewis structure picture is a sigma and a pi bond. It's actually way more complicated in the MO theory picture, but the highest energy orbital for oxygen, there's actually 2. They end up being pi stars, the highest energy occupied, highest occupied molecular orbital, and they each only have 1 electron in them. If you want to see how this works out, just Google the MO picture of oxygen. You'll be taken back to a PTSD moment from Gen Chem where somebody showed this to you, and just like the vision of the outer darkness, you asked the Lord to close up the vision very soon so that you could stop worrying about it. So here is the highest occupied molecular orbital of oxygen. This is the triplet state. You don't need to worry about that, but that is the state at which the 2 electrons have the same spin. There's an alternative state where they have opposite spin. That's called the singlet state. And the singlet state is higher in energy and more reactive. And so it's thought that you need the ignition, a flame of some kind or a spark, in order to excite molecular oxygen from the triplet state to the higher in energy singlet state. And then that singlet state is very reactive, and it's essentially a diradical. Okay, so we've dealt with oxygen, ignition, and fuel. Now let's show what happens once you light that spark. So one of the earliest steps, and drawing the Lewis structure for singlet oxygen is hard. We're going to basically do it like this, though this is inadequate, but it at least shows you the unpaired electrons. The simplest step is probably hydrogen abstraction from your hydrocarbon source. A radical on the oxygen steals a hydrogen atom from methane, and you leave behind a carbon-centered radical. And this is why oxygen is so good at combustion, because after you've done hydrogen abstraction, you've got a new oxygen-hydrogen bond, and this is called the peroxy radical. But you've still got 1 radical left over on the oxygen, and in addition, you've just made methyl radical. So that's definitely one of the reactions that's going on. If you look at what we need to do overall, we need to oxidize the carbon by decreasing the number of CH bonds and increasing the number of CO bonds. We've just removed a hydrogen, but now how might we increase the number of CO bonds? And it turns out that the methyl radical can find a peroxy radical and make a new carbon oxygen bond, and that's methyl peroxide. And there are a bunch of other things that can happen. In fact, I've got a list of, beyond this point, 1, 2, 3, 4, 5, 6, or 7, reactions, but it literally is 7, that go to get from methyl peroxide to CO2. Now, I assume at this point you got the idea and you don't necessarily need to see them all. If you want to see them all, come talk to me. But that's even that is just a fraction of what's going on in a flame. Okay. Questions? Plastics. Should we do plastics? Yes, we should totally do plastics. But before we do that, I want to tell you what actually you're seeing when you look at a flame. So if you burn natural gas, you know that the flame is blue. The reason it's blue is because one of the intermediates in this complicated reaction is called methionine radical, and another one of the intermediates is a weird carbon species, neutral carbon species called C2. Both of these get excited by the heat, and then they relax, and when they relax, they shoot off a photon of blue light. So when you see a blue flame, you're literally seeing methionine radical and C2 being excited and then giving off light. What about yellow color in flame? The yellow color is what's called incandescence. That's a fancy word for black body radiation. Why am I writing the word fancy? Black body radiation. This is something you maybe learned about in physics. It's that hot things glow. So one of the products of fire is soot and ash. You can actually get some of these methionine radicals to create longer hydrocarbons. And that those particles of soot and ash will get really, really hot and they will glow, which you've seen if you've ever heated up metal on a stove and seen it start to glow. So the yellow color in a flame is just particles that are glowing because they're so hot. All right, plastics. So radical polymerization is used to make plastics, a lot of plastics. And we'll talk about this more in 352. There's so much more we could do. But I'll show you an example of a particular radical polymer. A polymer is composed of many repeating subunits, and the subunits are called monomers. And you will see that the structure of the monomer directly influences the structure of the polymer. This monomer is called vinyl chloride. The polymer, we're just going to zoom in on a section of the polymer. The polymer looks like this, and it has two carbons with a chlorine attached to it, to one of them, and then another two carbons, and then another chlorine, and then another two carbons, and another chlorine, and then another two carbons, and so on. You get this repeating pattern, and that's characteristic of a polymer. All right, and the red lines here indicate bonds between individual monomer subunits. How does this happen? Well, you need a radical initiator, and then that radical can attack a pi bond. So this is radical addition to a pi bond. You can think of this as the radical attacking the pi star, or you can think of this as the pi bond attacking the radical. But basically, you're going to form a new sigma bond between the radical and one of the electrons in the alkene, and then the other one is going to end up on the other carbon. This reaction is regioselective for putting the radical on the carbon that has the chlorine, and that is because the carbon that has the chlorine is resonance stabilized. Lone pairs on the chlorine can spread out that radical. And then, once you've done that, carbon-centered radical can then do the same thing with another monomer, and you end up with now the slightly longer polymer. And I think you can see how we could repeat this multiple times to get a much, much larger polymer. The size of that polymer is going to depend on basically how much monomer we have and how much radical initiator we had per monomer. If you have a ton of radical initiators, you start a ton of polymer chains and you run out of monomer more quickly, so the polymer chains are shorter. If you have fewer radical initiators per monomer, then you start only a few chains and the chains get quite long before you run out of monomer. The identity of the group that's attached to the alkene influences the structure of the polymer. So what we have here is a polymer called polyvinyl chloride, which you probably have some experience with. If you say to somebody, dude, you want to come over and listen to my vinyl? You probably never said that. But my kids are like big on owning records now. I don't know what the deal is, but like we fought long and hard to get rid of our records and put them on our phones so we could listen to them, and now people want to listen to music on records again. So, okay, great. But anyway, the records are made out of plastic vinyl, polyvinyl chloride. That's why they call it vinyl. Also, if you've ever done anything with sprinkler systems, PVC pipe is a common way to do this. If you see on a label of a particular plastic, the recycling code 3, that is for PVC. It's used a lot for pipes, fittings, hoses, and flooring. PVC can be somewhat brittle. It doesn't expand very well with temperature. So I've had, if you've ever, people that are from Wisconsin or the Midwest or perhaps even the East have no concept of irrigation. Like it just rains there and it's fine. Out here in the West, we gotta water the lawn if we want it to live. Why we should have a lawn in the first place doesn't necessarily make a ton of sense. But when we moved into our house, we had to put some sprinklers in, and I was told every winter you must blow out your sprinklers with compressed air to remove the water, because otherwise the water will freeze, it will expand, and if it expands inside the polyvinyl chlorine pipes might burst. So I did that for the first couple of years we were in our house, and then one year I was just kind of lazy. It got to be November and I hadn't done it yet, and I'm like, it's probably fine. I mean, how many times in your life have you said, it's probably fine? So many times I've said, it's probably fine. It was probably not fine. Because do you remember the story in Ezekiel where water flows out from under the steps of the temple, and you get so far and it's ankle high and then knee high and it goes and heals the world? Well, we didn't heal the world that day, but we definitely had water coming out from like the whole lawn lifted up, and water was pouring down the driveway. There's this 10-foot long thing of pipe that had just shredded with the water, and I haven't made that mistake again. So let that be a lesson to you. Be sure to blow out your sprinklers. Is that the moral of the story today? So that's PVC. Now, if you change the monomer structure slightly, we're going to keep the same basic framework. Why can't I select all of that? Okay. Keep the same basic framework, but lose the chlorine. Now your starting material is not called vinyl chloride, it's simply called ethylene. Erase the chlorines, they're now replaced with hydrogens. This is now just a hydrocarbon chain, and it's called polyethylene, or PE. And there are a few different varieties of PE. There's high density polyethylene, which is pretty rigid, and that's recycling code 2. And then there's low density polyethylene, which is recycling code 4. And low density polyethylene is a lot more malleable. You can use it for water bottles and other sort of plastic bags. It's transparent. High density polyethylene is more of the rigid plastic containers like you'd use for laundry detergent or whatever. Okay, there's more to say there, but I think that's enough. Polystyrene is another example, but we'll talk about that more in the chapter on polymerization 352. With that, happy Thanksgiving. I will see you in a week.